there is the first change is that there is a change in S or in the input data structure. And this you have to reflect the output will change naturally. And what we have to do is to go via an AC0 circuit. An AC0 circuit is just a constant depth circuit with unbounded fan-in ands and others. And sorry. So unbounded fan-in ands and others. And in order to do so, you require some auxiliary data which you have stored, which stores what was so the current state of the algorithm, and you can use much of it, and we'll see how. So from the input, you send your input to the AC0 circuit, which also takes the auxiliary data into account and outputs the correct value. And in fact, you would have to compute the auxiliary data as well. Right? So basically, the idea is the input is evolved with time. At every step, you have to output some value. In this case, the span of S. And we do this by using a small circuit and auxiliary data, a small depth circuit and an auxiliary data. Okay, so we'll see how the data is organized and so on. Notice that we do not know how to do membership problem in AC0, but we can make AC0. That is the crux of the thing. So you can improve the performance of the algorithm by using dynamism. So we don't have to recompute everything from scratch. And yeah. So what is a brief history of parallel dynamic complexity? So initially it was introduced by Mack and Newman in the logical context. First order, so DIN first order is what DIN FO stands for, and we refer to it as DIN AC0 because they are entirely equivalent apart from uniformity, and we will assume uniform circuits. So yeah. So one can think of the algorithm as being a dynamic algorithm. So dynamic algorithms usually measure progress in terms of the time they take for updates and changes. And here we measure it in terms of complexity classes like AC0. So there are many problems which are known to be in DIN FO by now. They include reachability, regular path queries, and so on and so forth. And yeah. So there is an important parameter that is associated with in dynamic complexity, which is the number of changes in one step. So in the simplest model, there is a single change at every step. Only one element changes, but you could allow a larger number of changes, and still you want to put it in a small class. So we will see the algorithms that I present today will concern single changes and polylogarithmic changes. So we will not optimize on the work of the algorithm, which is the processor time product. We will only concern ourselves about constant depth while using polynomial processors in the CRCW framework, or polynomial gates in the AC0 framework. So what are our results for commutative monoids and the set S? We present a DIN FO algorithm or DIN AC0 algorithm for single changes. And this can be generalized to abelian groups where we require inverses to see that the span can be maintained in randomized in AC0 under polylog changes, and also in deterministic AC0 under slightly sublogarithmic number of changes. Notice we have, okay, so let me, so another thing that we see as an application of this result is that isomorphism between groups, abelian groups, can be maintained in AC0 under the same number of changes and so on. And finally, I've been talking about changes only to the S, the set, but actually we can also make sure that we allow changes to the table. And I will not cover this in this. So let's move on to CGM for commutative monoids. So monoids, as I said, where you don't require inverses in monoids, and otherwise they have associativity and identity. Dynamic monoids. So how do we solve the dynamic monoid problem? And what is the dynamic monoid problem? You are just given monoid and a set S, and you want to know what is the submonoid of M, which is spanned by S. You take all the products and so on. You want to know whether a particular element is there or the entire set is. What is the entire submonoid that is spanned by? The idea is to use a T data structure. It's a very simple algorithm. So what is the static data structure that is that we create? So we will first create a static data structure that will be used as the auxiliary data, and this consists of the method is given as A1 through AN, and what we do is to build a complete binary tree with n leaves. Correct? So it's empty only in the last level, and you pre-compute for each A the powers of the elements in the monoid. So that you can pre-compute by in EC1 or whatever, or in CRCWP RAM with log n time. Then you associate. So the basic idea is you just associate with each node a set, which is the set spanned by the elements contained in the subtree below it. Correct? So, for example, mu is PA for mu being leaf, and it is the empty set for anything not in S. On the other hand, for internal nodes, the non-leaves, you take the product of the submonoids generated by the leaves. Correct? So you take the product of the two that you get from the two children, and then the submonoid, it's easy to see that the submonoid generated at the root is the span of S. So it's a very simple data structure. We will need to augment this slightly for dynamic algorithms, but so how do we do this for dynamic data in the dynamic setting? We maintain this mu for each mu for each internal node mu, and also we maintain mu sub mu. So for two nodes, such that they are one is a descendant of the other, we would maintain this mu given mu. So that is, if mu is set to 1, mu is set to 1, or the identity monoid, then what happens? So for example, here is this mu and mu, and here I created a sort of a gap in the tree by setting mu to 1. And I maintain what is the value of mu given mu if I set this mu to be 1. Correct? with these two things, I'll show how to maintain the CGM problem. So how is it maintained with these two? The idea is, this should be on the slide. Slides are missing. Never mind. So, the idea is that so, so when a node is inserted or deleted, insertions are easy to do because they occur only you can add them at the root, and it's easy to handle them just by taking a product and so on, building another tree for them. Another complete binary tree, and since there are only thousands of them, since there is just one of them, you can do that. There's just one insertion. On the other hand, for deletion, you would have to take the least common ancestor of the deleted node. So you want to update. So firstly, when you delete the node A, you know that n mu colon A is the current monad when A is deleted. So think of the value. On the other hand, you have to update this mu given mu whenever A is deleted, and for that you take the LCA of A and M, A and mu, and where the need to do a quick update of those things. Correct? So I will not go into details because I'm not running very well on time. I will move on to polylog changes. So for polylog changes, the idea is you have this group and you want to make the polylog changes to the generating set. And you want to maintain the span of the generating set. And how do you do that? The idea is to use the data structure to maintain polylog size generating set for S. Instead, so compress S into a polylog sized set, and then use an independent generating set of the initial group to give a unique representation for each element of G. And finally, to use randomness to sample from this group and from this group, yeah, and see what this thing is, correct? So so we use the so we can compute the independent generating set. What is an independent generating set? Such that there is a unique representation for each element. There are no non-trivial relations between the elements in the generating set. So we know that there exists independent generating set of size logarithmic in every group, in particular for our group, and we will use this. So this is pre-compute. And now the randomized AC0 algorithm for computing S, for span of S, is just to take a random set of exponents, a random sequence of exponents, and compute xi to the beta n, where xi's are the elements of the generating set. And move on to the abelian group isomorphism problem. How much time do I have? 11 minutes. Oh, I thought I had 4 minutes. Sorry. So I'll go back. Okay. So I'll go back a little bit. Yeah. So we maintain a succinct generating set to support deletion. So how do we maintain the succinct generating set? We mm, uh, we sort of compute an independent generating set for G, the ambient group, and then for each element in our generating set, we can so we can replace it by these. Mm, so basically, it reduces to adding a polynomial many numbers, the polynomial many exponents, and that can be done in AC0. And this gives a randomized AC0 algorithm for sampling from the span of S, and therefore we can remove the membership problem. Now moving on to abelian group isomorphism. So we have given two abelian groups, G1 and G2, and with different multiplication tables, and you want to insert a polynomial elements from them, and you want to maintain whether the two groups are isomorphic under the changes, after the changes. So, and the changes are set, of course.
As we have seen previously, the SAT was quite strong and it was able to break logic locking. So to combat this SFLL was introduced. So what it does is that it introduces a cube stripping circuit.
Okay. Sorry.
They didn't know to wait for questions.
This was a question.
No, I think someone just joined the wrong
So, so the idea is to reduce this to several CGM questions that we saw how to solve in the previous slides. This is based on a reduction from McKenzie and Cook from a long time ago. Oh, yeah. Okay, that's fine.
Use it.
Okay. Okay. So doing the following crucial learning that suppose S1 and G1, S1 and S2 are two sets, and their spans are so S1 and S2 are two sets from G1 and G2, and there is so firstly we will reduce the problem to abelian groups. What are two groups? Two groups are groups where the orders are powers of P, and in abelian groups you can do this reduction. I don't have the time to get into this right now, but so you take the so here you have a criterion for isomorphism, which is that the two sets Sij, S1j, these are the powers of x to various p powers to the jth power is the same in cardinality as the corresponding set in the other case. And naively speaking, this would require a TCU computation to achieve, because we are counting the number of counting the size of the sets. We are comparing the size of two sets. But on the other hand, what we have is this following lemma, which allows us. This following lemma allows us to the counting part, which is that if you have a set given, if you have given sequence of elements, uh, the span of a sequence of elements, and let the size of the set be, so then the size of the set is T1 into T2 into Tr, where Tr is the smallest exponent, such that Gj to the Tj belongs to the rest of the set. This is again a result from McKinsey & Cook. And so this you can see is a CGM question, because Gj to the Tj you can compute easily, or pre-compute, and this is a CGM question. You want to know whether Gj to the Tj is contained in this thing, and by this you can get the value of Tj, the smallest Tj, which is a small number. And since the generating set is only small, you can log or log, whatever, you can add up logs, so you can add up the numbers in AC0. And therefore, we are done for this. So I reached to the conclusion of the talk. So here we have seen that the CGM problem and the isomorphism problem can be solved in AC0 for commutative monoids under single changes, under randomized AC0 for abelian groups, under polylog changes, and under sublogarithmic changes for using a deterministic algorithm, which I did not have time to cover. There are analogous results for, of course, which we saw for the isomorphism problem. And what is the future directions for this? Can we extend the results to non-abelian groups like nilpotent and solvable groups? And what about permutation groups? So with that, I conclude the talk. Thanks.
First question to the audience. If you're given two abelian groups with n cross n multiplication tables and you're asked to check if they are isomorphic, how much time would you take? Okay, Dara is not a good person to answer this. Okay. Okay, then I'll ask a PJ instead. So when Niels Henrik Abel was a grad student, did he used to stay in the hostel or was he staying far away? He probably commutes, right? Okay. Anyway, we'll open there. Okay, we'll open up for questions. Any questions for Sunny? Yeah, I have one question. So when you were talking about changing the multiplication table, how do you do that in a dynamic fashion? I mean, like,
so you don't change the multiplication table. You just observe that near a multiplication table there is exactly one group. So the radius, the distance of multiplication table, a given multiplication table to a group multiplication table is at most, I mean, basically two groups differ by at least n by log n or some such. So you can think of just working with the static group and can change this periodically. You can, if there's enough time to recompute the changes in the for the other groups. So yeah.
For general groups like nilpotent and solvable, anything better is known than the obvious one. Like, if you increase the
setting, I am not aware of it. I don't think so. Sorry. Yeah, Dara mentioned. Yeah,
multiple groups like solvable and all these things, what will be the obvious thing? Like the question of,
I mean, log space is obvious,
yeah, of course, but
but so that is bin AC1. Bin AC0, between bin AC0 and bin AC1, I do not know how.
okay.
Yes.
Other questions? If not, let's thank Samir.